Welcome to Part 2 of Compass Directional Guidance's Resistivity Lunch and Learn series. In this online talk, we will introduce Compass Directional Guidance's new dual lateral log resistivity tool, the LL5. In Part 1, we covered the importance of formation resistivity and how to use Archie's relation to determine oil saturation. Archie's relation is used to estimate the water saturation, SW, of a zone of interest. Two quantities are required. The first is referred to as R0 and is an estimated resistivity that represents the hypothetical resistivity of the zone of interest if it were 100% saturated with water. R0 in the oil-bearing zone cannot be measured directly since it's mixed with oil. Therefore, it must be estimated from the resistivity of a nearby water zone with similar geology and water salinity to the zone being evaluated. How this is done was discussed in Part 1 of the Lunch and Learn series. The second quantity is the actual measured resistivity of the formation by the tool, referred to as RT. The water saturation is then calculated by taking the square root of the ratio of R0 to RT. Oil saturation is calculated by subtracting the water saturation, SW, from 1, since water saturation plus oil saturation must equal 1. While there is some varying degree of uncertainty in this calculation, it has proven to be a good enough foundation upon which to build a large hydrocarbon services industry. In this talk, we'll focus on a new resistivity tool based on Ohm's law. These tools are sometimes referred to in the literature as galvanic or lateral log tools. These tools must be in direct ohmic contact with the borehole mud and formation. Therefore, their application is limited to conductive water-based muds. By way of review, Ohm's law says that if I apply a voltage V across a lump of material, the amount of current I that will flow through the lump is proportional to the voltage and inversely proportional to a property of the lump called resistance. Resistance is an extrinsic property of the lump because it depends on the size and shape of the lump times the resistivity of the material. Material resistivity is an intrinsic property of the material in the lump and does not depend on the dimensions, only the material itself. The diagram in the lower right corner of the slide shows a cylindrical lump of material of resistivity ρ, length L, and cross-sectional area A. The electrodes are not shown, but assume that the voltage would be applied between the two flat circular faces on each end, so that the current would flow parallel to the long axis of the material. The resistance between the two flat faces would be the resistivity ρ times the length L divided by the area A. In practice, a tool will apply a known voltage difference between at least two electrodes, causing current to flow into the formation. The injected current is then measured by some means. The ratio of the applied voltage divided by the measured current gives an apparent total resistance. It is converted into apparent resistivity by multiplying the apparent resistance by a geometrical or shape factor. The shape factor, or K constant, depends on the physical dimensions of the electrodes chosen by the tool designer. In the case of the cylindrical lump, the shape factor is the area A divided by the path length L. This means that the apparent resistivity of the lump is equal to the applied voltage V divided by the measured current I times the shape factor K. The key to understanding and comparing different resistivity tools is to ask and then answer, where do the currents flow? More specifically, where do the measure currents flow? The flow of electric current is not magic, it's physics. It always follows very specific laws of nature. This slide shows two current maps from a wireline dual lateral log tool. The current map on the left side of the tool corresponds to a deeper reading resistivity measurement. The current map on the right side of the tool corresponds to a shallower reading resistivity measurement. They are juxtaposed in this diagram to facilitate a comparison of the differences. Observe that on the left side of the tool diagram, the effective physical length of the guard electrode is much longer than the effective physical length of the guard electrode on the right side of the tool diagram. The longer guard electrodes force the measure current to return back to the tool much farther away from the source than do the shorter guard electrodes. Hence, the measure current beam goes deeper into the formation before spreading out compared to the measure current beam with the shorter guard electrodes. Please note that the tool does not broadcast both of these current patterns simultaneously. It will do so one at a time. It will make the shallow measurement, reconfigure the electrodes internally, and then make the deep measurement. Also note that the currents in these diagrams are shown in only 2 dimensions. In reality, the current flow out of the tool is radial in 3 dimensions. This is a close-up of the LL3 array. The center electrode is the measure electrode, sometimes labeled A0. The current that is emitted from the measure electrode is called the measure current and labeled I0. This current is focused so that it flows across the borehole annulus and into the formation. The focusing is accomplished by symmetrically arranging guard electrodes that are positioned above and below the measure electrode. The guard electrodes are driven at the same voltage as the measure electrode V measure so that no current flows across the insulating gaps between the guard electrodes and the measure electrode, thereby forcing all the current flowing out of the measure electrode to flow radially into the formation. Focusing is important because without it, a significant portion of the measure current would flow up and down the conductive annulus in the borehole and return to the neutral portions of the collar above and below the measure electrode. This would have the effect of reducing the apparent resistivity seen by the tool. The apparent formation resistivity, R apparent, is calculated using Ohm's law. R apparent is equal to V measure divided by I0 times the tool constant K. The tool constant K is only a function of the tool dimensions. Its value is determined by normalizing the response of the tool in multiple modeled formations. It is the shape factor that was referred to in a previous slide. This slide shows the effect of guard length on the depth of investigation. The plot on the left shows the current pattern using short guards. Overall electrode lengths of 2 guards plus a measure is about 4 feet. The plot on the right shows the current pattern using long guards. Overall electrode length is a little more than 9 feet. The white lines represent lines of current flow. The colors on the background represent the voltage. Red equals 1 volt. The darker blue color represents 0 volts. The longer guard electrodes focus the measure current deeper into the formation than the shorter guard electrodes. Both plots are on the same physical scale. Speaking very qualitatively, the depth of focusing or investigation for the longer array is about a factor of 2 times the depth of focusing or investigation for the shorter array. This slide shows how one might implement shallow and deep reading lateral log measurements into a single tool using a drill collar with insulating gaps. This embodiment uses 6 insulating gaps, creating 5 isolated electrode sections, hence the designation as LL5. The measure electrode M0 in the center of the array is about 22 inches long. Immediately on each side of M0 are the upper and lower short guards labeled upper guard 1 and lower guard 1. The guard electrodes are also about 22 inches long. The next pair of electrodes are the outer guard electrodes labeled upper guard 2 and lower guard 2. These are about 30 inches long. Beyond the upper and lower guard 2 electrodes are the upper and lower collar returns. This slide shows the electrical configuration of electrodes for the shallow or short guard mode of operation. For this mode, upper guard 1, the measure electrode, and lower guard 1 are energized with the voltage V measure. The current return is composed of the upper return, upper guard 2, lower guard 2, and the lower return. The voltage of the return sections are held at 0 volts. Current flows out of the 3 middle electrodes, fans out, and returns to the upper and lower return sections. The guard current is not measured. Its only job is to focus the measure current. Only the current flowing out of the measure electrode is measured and used to compute R apparent for the shallow mode. This slide shows the electrical configuration of electrodes for the deep or long guard mode of operation. For this mode, upper guard 2, upper guard 1, the measure electrode, lower guard 1, and lower guard 2 are all energized with the voltage V measure. The current return is composed of the upper return and the lower return. The voltage of the upper and lower return sections is held at 0 volts. Current flows out of the 5 middle electrodes, fans out, and returns to the upper and lower return sections. The guard currents are not measured. Only the current flowing out of the measure electrode is measured and used to compute R apparent for the deep mode. Now we can finally answer the question, where do the currents flow? Electric current prefers to follow the path of least total resistance. This path is a combination of the shortest and most direct physical route together with the lower values of material resistivity. The current doesn't flow exclusively in any path to the exclusion of the others. It divides itself among several different paths. The path with the least total resistance will support more current than a nearby path with more total resistance. For example, if I have a homogeneous formation of uniform resistivity, then the current will find the geometrically shortest route between the current source and the current return electrodes. For the LL5 tool, the guard current will be the greatest across the upper and lower insulating gaps between the ends of the guard electrodes and the beginning of the collar return. If I now add a borehole between the tool and the formation filled with low resistivity mud compared to the formation resistivity, then the current flow will give more preference to the borehole than it will to the more resistive formation. Unguarded measure currents will be dominated by the borehole diameter and borehole mud resistivity. The curve may wiggle, but it will be far from quantitative. To counter this borehole effect on the measure current, tool designers added guard electrodes on each side of the main or center electrode. Only the current from the center electrode is measured, hence it is commonly referred to as the measure electrode. By definition, guard electrodes are operated at the same voltage as the measure electrode so that the measure electrode current cannot flow up and down the borehole. The guard current flows up and down the borehole and into the formation, but the measure current will be strongly focused in a radial direction into the formation. This active guarding greatly reduces the borehole effects. An insulating gap by itself does not prevent the measure current from flowing up and down the borehole and is not a substitute for active guard electrodes. This slide shows a model log comparison of the resistive and conductive 4-foot thin bed responses for the dual LL5 resistivity tool and a very generic 2 MHz propagation resistivity tool. In the conductive water sand, the propagation resistivity tool does a better job of reading the conductive bed. In the more important resistive pay zone, both LL5 curves do a better job of reading the bed resistivity. Looking at only the 2 LL5 curves in both the resistive and conductive thin beds, the LL5 deep measurement does a better job of reading the bed resistivity than the LL5 shallow measurement. This is because the deep curve with long guard electrodes remains focused farther into the formation than the shallow curve with short guard electrodes before the current fans out into the more conductive shoulders above and below the thin resistive bed. Hence, in this case, the shallow reading measurement exhibits more shoulder bed effect than the deeper reading measurement. However, in a long horizontal drain hole, both curves will generally agree with each other unless the wellbore trajectory approaches a conductive bed boundary or if there is conductive invasion, indicating high formation permeability. Using the two curves together will enable better well placement relative to both bed boundaries and formation permeability. This slide is a summary of the LL5 measurement features. The target is the low-cost, high-volume market comprised of slim holes and salty water-based muds. The tool will not operate in oil-based muds. The tool offers two distinct depths of investigation. This will permit the detection of conductive invasion, and in simple cases in resistive beds, it may permit the determination of the radius of invasion if the invaded zone resistivity can be known from other local knowledge. The resistivity measurement will exhibit the same vertical resolution regardless of the depth of investigation. The inner probe is fully retrievable. It combines with the compass directional guidance MWD module that includes a mud-operated pulsar, batteries, direction and inclination, and plateau gamma ray. It is available in collar sizes of 3 3/4, 4 3/4, and 6.5 inches. For more detailed explanations of resistivity measurements, a short list of references has been provided to help you get started. The first two are textbooks and may be purchased from most online resellers. If you would like more information, you may contact Kelsey Long at the contact numbers listed on this website. Thank you very much, and this concludes the presentation.